Okay, so here's where we were last time. Y'all will recall we were considering this question, this kind of sort of vaguely Wronskian-like question of, hey, suppose you have a list of vectors, how do you decide if they're independent or dependent? And let me just remind you that the Wronskian itself, well, the Chapter 2 Wronskian that we talked about way back when, was an attempt to answer this question in a context that at the time we realized was hard. I mean, after all, if we were in Rn, this would be easy. Right? Chapter 1 tells us if you have a list of vectors in Rn, you want to decide if it's independent or dependent, easy games. Right? Okay. So the Chapter 2 Wronskian showed us that if you're talking about functions, then there's a certain game that you can play where you take the functions and you start taking derivatives and you assemble this matrix in a certain way. And by way of an argument that we made at the time, we showed that it allowed us often, sometimes anyway, to answer the question. So here we consider the question again in a much more broad circumstance. We're not in Rn. Not only that, we are not even necessarily talking about functions. This is just n vectors in any vector space. Okay, so much harder problem. I can't just say, take these things and start taking derivatives of them. I don't even know what they are. Okay. So the little homework assignment I gave y'all was to prove this result here, that if you have a dependent list, by the way, I know we don't know that yet, right? But hypothetically, if you had a dependent list, and if you plug them into a linear transformation, then the output's also dependent. So I hope y'all had a chance to think about that. The point is, if you have a relation between the input vectors, linearity allows you to directly find a relation between the output vectors. Okay. This is not, as it stands, all that useful because this statement here requires that we know the answer to the question that we're trying to decide, and that, of course, not very helpful. So here's where we pull a nice little fast one. We write down the contrapositive. Dependent inputs give you dependent outputs. The contrapositive then says, well, then if your outputs were independent, your inputs must have been independent. Okay, so this contrapositive is actually something that we're going to be able to profit from. Notice that this contrapositive is a statement whose punchline is an answer that I am hoping, at least sometimes, when this is the right answer, this is an answer that I would like to be able to conclude. And this is a conclusion. So what I'm lacking now is, how do I decide if the outputs are independent? And here is where it's convenient that I arranged that those outputs would all be in Rn. Right? So that's the clever move. The reason why we look for a linear transformation into Rn is so that this question will be old news. Right? These outputs in vectors in Rn, no problem. If you have n vectors in Rn, make this little construction here. Look at the determinant. Take those vectors, make a matrix, take the determinant. It's the oldest news in the world. Right? Determinant being non-zero tells you independent. So altogether then, here's how we're going to proceed. Given this linear transformation into Rn, any linear transformation into Rn, it results in this construction here. This is what I'm going to call a Wronskian-like construction. I claim that it's Wronskian-like because it is Wronskian-like because when it's non-zero, that means the images are independent, and if the images are independent, that means my list that I was initially interested in is independent. Clever idea, right? So Wronskian-like because non-zero means independent. Okay, so the beautiful thing about this is that this gives us, we can form as many Wronskian-like constructions as we want. All we need is Euclidean valued linear transformations. That's it. And you've got yourself a new Wronskian. Okay. So this Wronskian, this Wronskian-like thing, this thing here, What does this have to do with Chapter 2? In Chapter 2, our familiar old Wronskian was this thing. Well, notice all this is telling you then. This tells us what our linear transformation was. The linear transformation was that formula. If you take this linear transformation, not hard to confirm, y'all can do this on your own. If you take this specific linear transformation, plug into that construction in purple up there, you get the classic Wronskian. Okay. Take any other linear transformation, you get a new Wronskian. Okay, so here, why are we considering this? Well, because we're looking at functions, right? We've got potentially a list of vector-valued functions. And I would like to be able to decide, given a list of vector-valued functions, is this an independent list or is this a dependent list? How do I decide? Vector-valued functions do not fit the form that we previously dealt with. If let's go back down to the Chapter 2 Wronskian. Here it is, our Chapter 2 Wronskian. If this thing here and etc., this thing here, if those things I have in blue are all individually vector valued, I've got, if I follow this rule and start taking derivatives and try to sort of stick everything in there, I've got too much stuff. It doesn't make a matrix. There's not enough space in a matrix to put it all in there. It just doesn't work. Right? So how do we deal with that? Well, what we have to do then is we have to figure out, unlike our previous scenario where given a function, we had to take a bunch of derivatives to create a vector. What do I have to do to a vector? What linear process can I do to a vector to make a vector? How about nothing? Just leave it there. Right? Let's apply the identity linear transformation. That is linear. It's easily confirmed to be linear. And what you get is our new Wronskian for use with vector-valued functions. Right? If you have a bunch of solutions that look like this to one of these kinds of differential equations, just one at a time, take these vector-valued functions, make those the columns of your matrix, take the determinant. That's the Wronskian for this context. Okay. We could spend a bunch of time on this that we won't. What I am going to do is jump to another nice punchline. There is a revised version of this Wronskian. Recall that we saw in Chapter 4, if you're looking at one of the Chapter 4 differential equations, if you're looking at a list of solutions to one of the special kinds of differential equations, that additional information makes your Wronskian stronger. And the same thing happens here. If you're looking at a list of solutions to the same kind of, this is Chapter 6 kind, but if they're all solutions to this same differential equation, linear first order system, coefficient functions being continuous, then we get the same convenient answer that we got back in Chapter 4, and that is the Wronskian is either always 0 or never 0. You'll probably remember that from Layton 4.1. And furthermore, those correspond to dependent and independent, respectively. Okay, easy example. You may recall this differential equation. This was the first differential equation we looked at. And I just wrote down a couple of solutions. I pulled them out of thin air. Right? Rabbits out of a hat. I said, hey, look at this. That's a solution. How about that? And, oh, look what we have here. That thing there is a solution. I just conjured them out of thin air. And then I wanted to talk about the linear algebra of them and, make the linear algebra observations about, dimension and that kind of thing. So how do we know they're independent? Well, we got lucky at the time. These are, I'm going to say obviously independent because they are multiples of non-parallel vectors. This is a multiple of -1, 1. That one's a multiple of 3, 2. These are functions that are pointing in different directions. They're clearly independent. But let's pretend we hadn't noticed that. right? This will serve as a nice test case of our Wronskian. Does our Wronskian do what it's supposed to do? Well, let's see. Take those, make those the columns of a matrix, take the determinant, you get this. Notice that is never 0, and therefore our answer is independent, which again we already knew, but good sanity check for this Wronskian. How we doing? Questions? Okay, I want to point something out for y'all for you to consider. Going back to this discussion over here, I mean, where how we use this in solving these kinds of differential equations is this specific application. I mean, this specific new Wronskian, right? But there's a lot of vector spaces out there, and in general, and you might have different kinds of information about the functions that you're interested in. So, in general, you can use any linear transformation with vector-valued outputs, and depending on the information you have at your disposal, you might manufacture a linear transformation out of the scraps of information that you have. So I have some old test questions. Of course, y'all know where to find those. I encourage you to take a look at them. Pretty sure there's at least 2 of them. There might be more. I just don't remember. But all of those test questions consist of, I give you a bunch of information about a list of functions, right? And you have to figure out how to look at that various scraps of information that are given about these functions and decide what parts of the given information are linear and what parts aren't, right? And with the given linear transformations, you can assemble your own linear transformation, construct with that linear transformation your own Wronskian-like construction, and use that to decide if the list of functions is independent or dependent, or at least if they're independent. Okay, so like I say, there's some old test questions on that. I encourage you to take a look. It'd be a good practice in understanding these ideas. Okay, so moving along to section 6.2. Reminder, there's very strong analogies between Chapter 4 and Chapter 6. We've seen a lot of those already. The next one that we're going to see is just kind of in the progress of our study of these kinds of differential equations. In Chapter 4, we spent the first section kind of defining strategy and fundamental theorems and that kind of thing. And then we went on in 4.2 to look at the homogeneous case. Well, here we are again, Chapter 6. We spent the first section talking about kind of, tools and, laying the groundwork, strategy, that kind of thing. And here we are now, we're going to look at the homogeneous case. Remember that homogeneous means that there's nothing there. There's no G. And we're going to talk about how to solve these kinds of systems. One thing that is different, it turns out to matter very dramatically whether this matrix is or is not diagonalizable. So we're going to start off in section 6.2. We're going to assume that this matrix is diagonalizable. At the moment, not clear why that should matter. It's going to matter dramatically, as it turns out. But at the moment, it's not clear. Section 6.3, we're going to consider what happens if the matrix is not diagonalizable. Right? So the comparison between the chapters is not perfect. We're going to spend 2 sections on the homogeneous case here compared to 1 in Chapter 4. On the other hand, the one in Chapter 4 section 4.2 is kind of huge. Okay. Okie dokie. Also, constant coefficient. Right, just like in Chapter 4. Alrighty, with that said, what can we do with diagonalizability? We know that diagonalizability means we can do a basis change and we can make it easier to understand the matrix. We can make it easier to understand the linear transformation that the matrix represents. So, right, sure, okay, fine. Will it help us understand a system of equations? Turns out it does. Here's how that works. It's very straightforward. If you have a diagonalizable matrix, you can write that a couple different ways. You can write that a bunch of different ways, actually. Diagonalizable means conjugation to diagonal. Right? Alternatively, it means change of basis to diagonal. Also fine. Don't forget, furthermore, diagonalizable also means there exists an entire basis consisting of eigenvectors. So different ways to say the same thing. Here I'm going to work with conjugations, and I'm going to take our system and just plug in the appropriate conjugation, right? I'm just plugging that in there, and notice that our system there turns into this, which does not seem to help at a glance. But here's what you do. Neat move. We're going to take this P right here. I'm going to whip it over to the other side. Becomes a P inverse, of course. So it becomes this. And then we say, hey, how about, notice that I've got P inverse Y over there, and I've got P inverse Y over here. Let's do a substitution. Let's let P inverse Y be a new vector valued function called Z. At which point I have Z prime equals DZ. This D is the only matrix left in there, right? And I have now a new system. You might call this a diagonal system. Okay, now is everybody good with that first part before we go on? Does everybody see what happened? It's explicitly the fact that we have a conjugation here that allows us to pull this move, do a substitution, and result in a diagonal system. All right, who cares? Right? So this matrix is diagonal. What is that bias? Don't forget this notation here, this vector notation for a system of equations. It's just a shorthand, or it could be, it's kind of a shorthand. But don't forget what the system actually is. The system is made up of a bunch of individual equations, and let's write that all out. What is the first equation? The first equation, Z1 prime equals, okay, now I'm going to have to take the first row of my diagonal matrix, and those are my coefficients that I multiply by the components of Z. So I'm going to have the diagonal entry lambda 1 times Z1. And then I'm going to have 0, Z2, 0, Z3, 0, Z4, et cetera, to all zeros. Likewise, in the second equation, Z2 prime is going to have just lambda 2, Z2, et cetera. In fact, what I end up with is a bunch of equations that all look kind of like that. Does everybody follow the sort of multiplying it out there? Everybody on board? Now, let me remind you why this was a hard problem in the first place. Let's look at, I forgot I already had this. So here's our system. We're looking at the homogeneous case, so forget about the G's. Here's what our system looks like. The thing that made these equations hard is that I can't solve this equation for y1 because this equation that has y1s in it also has a bunch of other junk in it, like yn, for example. I can't solve for y1 yet. I've got yns in my y1 equation. And worse than that, I also have y2s and y3s. I've got a bunch of other unknowns. I can't just solve for just the y1. That's why this was hard in the first place. And now, though, because of this diagonalization, I don't. Right? Very powerfully, in my Z1 equation, it's just Z1. There's no Z2s in there. There's no ZNs. Just Z1. I can solve that for Z1. Likewise, in the Z2 equation, there's nothing but Z2s, et cetera, et cetera. In the Zn equation, there's nothing but Zn's. These equations have been what we call decoupled. Reminder. Here, let me color code better. Decoupled. The ugliness of having we have our Z1 equation, but it's got Z2s in it, and there's Zn's in my Z1 equation, and everything's involved in everything else, and this is my little hand gesture to kind of indicate that, all these equations are intimately bound up with each other because each one of them involves functions that are also involved in all the others, right? So we have this, as I like to call it, rat's nest of connections and couplings, pairings, connections between the different equations. This is why the problem was hard. Now, there's no more rat's nest, right? We have untied everything, and all the equations are now just independent equations. Thus the term decoupling, right? So it's kind of all over but the shouting, really. I mean, I'm going to want to write some for your future convenience. I'm going to want to kind of play it out. And, let's take a linear algebra point of view on this and see, what the solutions finally look like. But we definitely see daylight at this point. Everybody on board? I mean, you could do it from here. Each one of these equations is Calc 2. Natural growth equation. Totally doable. Okay. Reminder, what allowed us to decouple? It was the fact that the matrix here is diagonal. How did we get that to be diagonal? Well, by doing a substitution. What gave us this idea to do this substitution? Ultimately, it was the fact that this was a conjugation. I rewrote A as a conjugation with a diagonal matrix. In other words, the thing that made this all work out is the fact that the matrix is diagonalizable. All right, so there's several steps in the process, but ultimately, this is why diagonalizability in the system allows you to solve it. Just trace through the process. Okay. Couple of quick observations. Don't forget this matrix that we used for our substitution. That's our change of basis matrix. More specifically, the basis is the diagonalizing basis. It's the basis of eigenvectors. Right? So ultimately then, in the same way that eigenvectors allowed us to find a simpler way to understand linear transformations, right? Likewise, eigenvectors have allowed us to take a simpler point of view on a diagonalizable constant coefficient first order system of differential equations, right? So eigenvectors make a lot of things better. Okay, how are we doing? Quick pause. All right. Okay, so now let's finish the solving. So we've got this decoupled system here. A bunch of Calc 2 equations. They're all natural growth. Natural growth equations are easy to solve. Here's the answers. There they are. One at a time. Those are the solutions. Don't forget that each one of these then is one of the coordinates of our solution vector, our Z vector. Remember, we're looking at a vector-valued function. So there it is. From a certain point of view, you could say we're done, but there's a lot to be gained from moving a little further along from this. Let's take a linear algebra point of view on this. This is your general solution, but from a linear algebra point of view, it's nice to find a basis for our general solution. We know this is an n-dimensional vector space, but let's find those basis vectors. Said differently, let's write this as a linear combination. Not hard to persuade yourself that that's how you do that. Specifically, notice that this first one here, for example, I've got C1 times e to the lambda 1x 0, 0, all zeros, right? Which is e to the lambda 1x times our first standard basis vector e1. So said differently, this first coordinate here which you see there, motivates writing this vector as that vector. Right? And likewise for all the other coordinates. So this linear combination, this general solution becomes this linear combination. This being a linear combination with coefficients that and that give us as our basis these vectors there. So there's our fundamental set of solutions in kind of vector form. Easy to do linear algebra with. Yeah, everybody okay? Questions? Okay. Oh wait, it's really easy inadvertently to spike the football on the 2-yard line here. We're not quite done yet. Remember, this is the answer, but this is the answer to the other. This is the question, the answer to our new question. This is our answer to our Z question. Our original question was not to find Z. We made this up because it would be easier and because it connects back to the question we're actually interested in. This is what we're actually interested in. We want to solve for Y, not Z. Right? So don't forget, you've got to convert back by plugging back into the substitution. Once you know Z, solve for Y, just multiply by the P matrix, no big deal. But you do have to do that. Do y'all remember back in Calc 1, I'm sure we've all made this mistake at least once in a Calc 1 class of, you have some integral you're working on and you do a substitution and everything lines up and falls into place and you do the antiderivative and then you put a box around it with a smiley face but you forget to substitute back in. Right, this is just like that. Don't forget to substitute back in. So that said, here we go. Substituting back in. I need to take these Z's. These are a bunch of Z's. I need to multiply by the P matrix. Here's our P matrix. Don't forget P is the matrix that we use to conjugate A to make it diagonal. So this equation up here is just our diagonalization equation. Just as a reminder of where P is and what it consists of. Don't forget the columns of P are the eigenvectors. Right? So what we're looking for then, our Y vectors, our fundamental set of solutions for Y are just, I'm going to take my P matrix full of eigenvectors and I'm going to multiply by these Z vectors up there. Well, look at the Z vectors. These Z vectors are mostly made up of standard basis vectors. Right? Standard basis vector, standard basis vector. We're pretty much there's scalar exponential functions there, sure. But those are scalar valued, no problem. As far as the vector part goes, standard basis vectors times a matrix whose columns I understand. And chapter 1 tells us that when you multiply like that, these Y's then are just those columns. Let's see, let me zoom out one. Here we go. Just these columns. You get the columns of the P matrix, namely the eigenvectors. Yeah? How are we doing? Everybody happy with that? Last step. And now we're done with this solution. There's a lot of little steps in the process, but ultimately, nice answer. Our fundamental set of solutions to our original equation in the diagonalizable case involves just taking the eigenvalues, making those coefficients in an exponential, taking the eigenvectors, multiplying said exponentials times said eigenvectors, and there you go. Now, I phrased this as a calculation, a for example, here's a differential equation. Let's solve this one. Let's see what happens. But notice, I didn't have any conditions on this other than diagonalizability, right? So what we have in fact done is proved a theorem, inadvertently. If you have any diagonalizable homogeneous system like this process shows after some effort, that your solutions are always of this form. And so here it is as a theorem, and y'all may cite this theorem. You don't have to go through the process every single time. If you have a diagonalizable system, if you know the eigenvalues and the eigenvectors, respectively, the eigenvalues go there and there, the eigenvectors multiply by those exponentials, and that's your fundamental set of solutions. Every time. Isn't that nice? All right. Flashback to section 6.1. You may recall that, again, I was trying to emphasize the importance of the linear algebra, and so I wrote down this differential equation, and I wanted to talk about, well, here's a couple of solutions, and I wanted to talk about the linear algebra of it, dimension and independence and fundamental set and general solutions and all that business. So I wanted to focus on the linear algebra, so I deliberately concealed where did these come from. Right, and I said, don't worry about it. We'll fill that in later. Right? Right now, let's focus on the linear algebra. So here we are later, and this is where those solutions came from. They came from observing that I know the eigenvalues for that matrix, -1 and 4, and I know the eigenvectors previously computed long ago of that matrix are that and that. And you'll notice this is exactly the solutions that we wrote down back in that discussion. Okay. All right. Okay. What if you have complex eigenvectors and eigenvalues? Well, the theorem still works. So here's a fundamental set of solutions. Note that the same deal. So our eigenvalues, our eigenvectors. Right, same deal still works. This is a perfectly fine, I suppose, fundamental set of solutions, at least from a math standpoint. These are solutions. There are 3 of them, right? But of course, we don't like them. This is an undesirable fundamental set of solutions because, well, they're complex. I mean, if this equation came at us because of a real-world application, involving real things like masses and springs and that kind of stuff. Well, complex valued solutions are, my yardstick doesn't have complex numbers on it, right? So it's seemingly not a helpful solution. Just like we did back in chapter 4, when you have a conjugate pair, such as we have here, conjugate pair of complex valued solutions, you can instead replace them with real and imaginary components. And so all we're going to have to do at this point is just look at one of these things, identify its real and imaginary components, and declare those to be our sort of, our in trade from our original conjugate pair. Okay, so looking at this function here, we just need to figure out how to write it in rectangular form, find the real and imaginary parts. And now it's just a little bit of complex algebra, no big deal. Let me zoom one notch. Here we go. So here's what's hard about that function as it's written. This is how it comes out of the theorem, of course. There's the eigenvalue. This is the eigenvector. What's hard about it is this first factor is what you might call in polar complex form. The second factor, now that's a vector, but that said, the coordinates are all in rectangular form. So we have sort of polar and rectangular, and there's no easy, convenient way to multiply polar times rectangular, leaving them in that form. So let's just convert both into rectangular form. So this, of course, already in rectangular form. Don't have to do anything to that. This factor here of e to the x, that's just real. That's not hurting anybody. Right? And so all we're really going to have to do is take this, the e to the ix, write that in polar form using Euler's formula. That's our first step. and then just kind of FOIL it out. This is the same kind of foiling that we did back in chapter 4. Of course, the exponential comes along for the ride. Nothing happens to that. Looking at let's talk about how to find this real part from this product. Real comes from real times real. You also get real terms from imaginary times imaginary. Don't forget I squared is -1. It's really easy to mess up those minus signs. So real times real, imaginary times imaginary, that gives us our real part of our product. And then the flip side is, let's see here, if we want to find the imaginary part of the product, well, I guess I better include that, the imaginary part of the product. Real times imaginary, and imaginary times real. And so there you go. So having the real and imaginary parts written out like that, we can replace this conjugate pair of complex valued functions instead with the real and imaginary parts that we just computed. And of course that first one, nothing happens to this guy. He just follows along. That's fine. How are we doing? Everybody follow? Okay, so that's the non-diagonalizable. Excuse me, that's the diagonalizable case. Now on to the non-diagonalizable case, and bad news. It does not work out as well. I hope that's not surprising, right? You remember we talked about diagonalization's nice. It's really diagonal matrices are nice. They have so many zeros, right? Everything lines up, and there's so many good things that you can say about diagonal matrices. So non-diagonalizable matrices are intrinsically a disappointment. And here's an example of our disappointment. Let's take our failed attempt to diagonalize. Remember, when you can't diagonalize, all you can do is Jordanize. So I can rewrite A as being conjugate to a Jordan matrix. And I can play this same move of let's take this P and move it over to the other side as P inverse, just like we did in the diagonalizable case. Let's recognize that this P inverse Y would be natural to rename as Z. But of course, Z is P inverse Y, means Y is PZ. Do that substitution, in other words. And that does get us down to this new system, but this new system, it's not diagonal. Of course, right? So this matrix is just not as nice. And let me show you what happens. I mean, explicitly, here's a numerical example. Let's look at this matrix A, and I'm going to give you for free here, and we'll talk about that. Where did this come from in a couple of minutes? But I'm going to give you for free this Jordanization of that A matrix. Free for nothing. Talk about the origin later. So you see the Jordan form. The original matrix is conjugate to the Jordan form, and we can take this conjugation and kind of do, put that in here, and et cetera, et cetera. And the resulting system is this. And it's not decoupled. It just isn't, right? The whole idea of decoupling is, all of these, there's each variable is in the other equation and everything's kind of linked together, and decoupling would mean that I would want none of the z's in any of the other z equations. But look, I've got z3 in my z2 equation. I can't solve for z2. I've got z2 in my z1 equation, so I can't start by solving for z1. So it's just not decoupled. The good news, though, I can totally solve for Z3. That I've got a foot in the door, right? That Z3 is decoupled from the others. You can solve for Z3, and once you solve for Z3, now you know what that is, and then you can solve for Z2. And once you know Z2, you can plug that into there, and then you can solve for Z1, and altogether, through this process, you've managed to solve for all of the Z's. Wouldn't it be nice if it was as simple as, eigenvectors? Right? That was the awesomeness that we get out of the diagonalizability. Here, we don't have that, awesome convenience, but we have like I say, we have a foot in the door. This is something you can solve. And in the absence of better tools, having a tool is pretty nice. All right. Okay, so this is called back solving, because you work backwards through the system. Right, I'm going to show you an example of this. We're going to solve this system right here. Start with the Z3 equation. Here it is. There's the Z3 equation. Good news. It's natural growth. There's the answer. Calc 2. Right? Okay. What do we do with Z3? We plug Z3 in there and then look at the Z2 equation. Okay, so there we're going to plug Z3 in there. We will look at our Z2 equation. How do you solve this? And oh gosh, it's not homogeneous. So this is a 4.3 problem. This is where things start to get a little annoying and tedious, but it's just a matter of being patient. The homogeneous part is quite straightforward. The homogeneous part is natural growth again, so you can write down the homogeneous solutions very easily. It's that non-homogeneous part. What do you do here? How do you find a particular solution? Go back to section 4.3. Write down your characteristic polynomial. Look at your right-hand side, write down your magic number. Again, per the theorem in section 4.3. There's our characteristic polynomial. There is our magic number, and you will notice that, unfortunately, we do have the unfortunate coincidence. Right? The magic number is a root of our characteristic polynomial, and therefore our naive guess would not have worked, so let's not try it. The naive guess, of course, would have been we look at this, and the naive guess would suggest that is our solution, but then the unfortunate coincidence has us stick in an extra factor of x. So I'm going quickly through that because I know I hope y'all all remember section 4.3. I'll make sure to brush up on that. Again, it's unavoidably important in this process. So this is the proper guess to make, and as usual, once you have the form of your guess, that guess goes in there. The equation becomes this. Work out details. That undetermined coefficient ends up being C3, and therefore, let's see here, homogeneous plus particular gives you your general solution. Yeah. Kind of a pain, but it worked, right? We've solved for Z2. Everybody on board? So reminder, we solved for Z3, plug that in there, then we solve for Z2, and then you're going to plug that into there, and this is what I'm going to leave for y'all to do on your own. It's the same process, more details, but then solve for Z1, and here's what that looks like. Again, I'm going to leave the details are y'all's, but it's just a matter of homogeneous plus particular. There is an unfortunate coincidence, so make the appropriate form of your guess, plug it in, solve for your coefficients, and then particular plus homogeneous. Same structural process, different details. Okay. Finally, assembling your answer together, you notice the first Z, we solve for Z3 first. Then we solve for Z2. I'm going to leave it to y'all to solve for Z1. Ends up being this. And those are the coordinates of your Z vector. Assemble them together. For linear algebra purposes, let's rewrite those. Instead of leaving this as just some sort of general solution, let's try to view this as a linear combination so that we can find a fundamental set. It's easiest to view this as a linear combination by seeing that these are going to be your coefficients in your linear combination, and therefore that, and that are your fundamental set of solutions. Whoops. Don't spike the football on the 2-yard line, right? Don't forget these are the Z's, right? This is not the Y's that we were looking for. Those are Z's. The Y's are, where did it go? Here it is. The Y's are P times Z, so don't forget that last step to multiply by the P matrix, and here you go, multiplying by the P matrix. Each one of these Z's, you multiply by P, and out comes your Y fundamental set of solutions right there. And there you go. So finally, a lot of tedium in it. It's like 3 pages of details, right? But it works. Okay. All right. Some quick comments about Jordan bases. I will go back and remind you that I pulled this out of thin air, the Jordanization, right? So in practice, day in and day out, how are you guys going to Jordanize matrices? Can you just rely on one landing in your lap, out of nothing? Well, of course not, right? So how are you going to do it? Well, as a general process, it's hard. It's something that's beyond what we can reasonably do in Math 216 in general. Years ago, I used to teach a special case in Math 216. It turns out if certain conditions are satisfied, then in that special case, it is highly accessible in Math 216. Go through a certain process and take some time to talk about. To find your own Jordan basis, right, in that special case. It's not in the book. The course is packed. And over time, I just realized I was covering too many things in the course, and I've since removed it. So there is that method, but you're not responsible for it at this point in Math 216. The only reason I'm mentioning it now is because you will find some old exam questions where previous Math 216 students were responsible for it. And so you'll see those questions and the corresponding answers. When you see those questions, just realize, hey, this does not apply to me. It's not my problem, right? And literally. And so you can just ignore it. Now, the details of exactly which questions can you ignore from these old exams, I'm going to send you all an email where I describe this in detail. Sometime in the next few days, probably not today, now that I'm looking at the clock, but probably tomorrow or Wednesday, something like that. Anyway, make sure to read that carefully. What you are responsible for, though, is knowing that if I give you some arithmetic, for example, this. Right, look at this arithmetic that I gave you. I didn't actually say here in that arithmetic, hey, here's the Jordan basis. Right? So you are fully armed to look at this situation and say, okay, well, look, this A matrix, that's representing T with respect to the standard basis. This J is representing T with respect to our mysterious Jordan basis, because you see it's in Jordan form. And therefore, this matrix, in this conjugating, inverses pair here, this matrix here must be change of basis from V to S because of how bases pair up, and therefore, because this is V to S, these columns must be our Jordan basis. So I do expect that you'll be able to make sense out of, identifying, given simply arithmetic with no labels, that you'll be able to identify, okay, what is what? And in this case, identifying that Jordan basis. Do beware. There's a temptation to say, I don't need to think about that, because you can see, hey, this is the one that's been inversed. Right? So two things. I will not always write it exactly like that. I might give you just a separate matrix over here. Different numbers, whatever. Neither one coming with an inverse, sort of label, sort of giveaway. And then you've got to look at this and say, well, wait a minute, are these columns my Jordan basis? Or are these columns my Jordan basis? Don't assume it's always the one on the left. Remember, sometimes D is given as a conjugate of A instead, or J is given as a conjugate of A instead of vice versa. And there's all these different cases, and don't memorize your way out of it. Right? Think in terms of what are the bases being used, and always check and always be careful. Okay, and we're out of time, so this is a good stopping point. See y'all later. See you on Wednesday. Have a good day. Now, okay. Just one moment.